Hello and welcome. In this video series, I'm going to show you how to turn this paper into this. So we're going to start from nothing and build an entire LLM line by line in PyTorch. What exactly are we building? What is this model described here? Well, there's a lot of interesting components being put together, but basically this is a model from last year. It's basically GPT augmented with memory. So in particular, we're going to be adding in recurrence, a vector database, k-nearest neighbors search, a new relative position embedding scheme, and a lot of other fun, interesting stuff. So if you've never implemented a research paper before, it can be very daunting. There's a lot to do. It's hard to even get a foothold to start. But that's what this series is for. So I'm going to guide you through this process step by step and teach you all of the things I wish that I knew when I first started implementing papers. And at the end of this, you're going to have an expert level grasp of LLMs, how they work in and out. We're going to follow data as it goes through every single stage of computation. And at the end, you'll know every single line what's happening to the data as it moves through the model. And in my opinion, and in Richard Feynman's opinion, this is the kind of level of understanding that you only get once you've taken something apart, put it back together again, and in doing so have been forced to confront every single detail under the hood. In addition, at the end of this project, you'll have the ability to start making your own ideas into working models. So while building this specific model is going to be fun and interesting, the real underlying point of this project is that you come away with a general process and a general framework for how to turn your own ideas into code. So this is going to be good practice that will give you the ability and knowledge to make your own ideas happen. Okay, some preliminary remarks before we get started. So I've created this series because there's lots of content on how LLMs work, how to use them, how to fine-tune an existing one. There are a million tutorials and courses and books. I didn't want to add on to that. There's a ton of great resources. But there's a conspicuous gap on how to build them yourself from scratch or open them up and start tinkering. So Andrei Karpathy videos are by far the best resource I've seen related to this. And if you haven't seen these are absolutely fantastic. You should check them out now. And this series is inspired by these videos, and it's going to be in a very similar format. So it's going to be hands-on, fun, I hope. We're going to demonstrate how every piece works. And I'd like to stop along the way every now and then to make sure that we understand conceptually what it is we're doing before we dive into coding. So if you haven't seen these, go check them out. If you have seen them, this series is a great place to continue from where he left off. As for prerequisites, this is a fairly advanced project, and I'm going to assume you're familiar with Python, PyTorch, and you should have a working familiarity with LLMs. So I'm going to explain what we do along the way in great detail. But if you're starting from absolute square one with deep learning, or you're a very early beginner, you should definitely find an easier project to work on. Before we start, there's one last thing I'll say that I think is incredibly important. So when you're watching the video, I'll be discussing some piece of the model before we build it, and then I'll go ahead and build it. When this happens, you should make a point to always try and pause the video and try to implement it yourself before you watch me do it. So if you just watch me do it without trying it yourself and struggling just a little, you're cheating yourself out of an enormous advantage. And this isn't a personal opinion. I'm not trying to get down on you. This is a very well-studied phenomenon in education and learning. And so I have a fun little example that I think helps demonstrate this. So this is from a book called The Talent Code by Daniel Boyle. And this is one of many experiments that kind of demonstrates this phenomenon. So take a few seconds to pause the video and look at the following lists of word pairs and spend the same amount of time on each one. Okay. Now, without rewinding or looking at the lists again, try to remember as many of the word pairs as you can. And ask yourself, from which of the two columns do you remember more words? So for most people, it's not even close. most people will remember about 3 times as many words from column B as they do from column A. The point is that just by this very tiny fumble where you have to fill in the missing letter, so just by a microsecond of struggling, it's as if you're tripling your memory. You're able to remember 3 times as many of these that you struggled with a little as you are with these that you simply read off. So the same applies for what you learn in this video, and as a broad strategy in life. If you just pause to think, reflect, try to do it yourself, try to come up with a solution beforehand, it doesn't take long and it has an outsized effect on your understanding, your memory, and your skills. Okay, onwards. Here's the main plan that we will follow. This is our example framework, our recipe that will guide us through this whole process. So, high-level plan. Pick a paper. Identify the idea, how authors implement it, how they test it. Identify the components of the paper, so the individual modules or classes or however you want to think about the major building blocks of the model. Develop a rough pseudocode understanding of how the model works and how these things fit together. And then you're actually going to get into it. We'll build the individual components. Lastly, we'll assemble them into a model, and then we'll run and test the model. So, step 1. I've already chosen the paper, but in the case that you want to build something else in the future, I have 2 pieces of advice. One is pick something you're very motivated to do, because implementing a paper can take a lot of time, and it can often be very frustrating. Related to that, point 2 is, if possible, choose something that has an existing implementation in whatever language or format. So, particularly if you're new to this, something to cross-reference your work is very, very valuable. And the other reason to do this is that details are often missing from a paper, and I really wish someone had told me this a long time ago. No matter how hard you look, sometimes details just aren't there. Sometimes the architecture and specs are simply forgotten, or it's assumed you know, or they're hidden somewhere in the code. So you won't be able to figure out how one piece of the model works just by staring at a diagram and guessing. And you won't know what hidden kind of hyperparameters were used during training to get a certain result. So this is just a fact that often these things are missing. And at that point, you have to guess, or you have to reach out to the authors and see if they're available over Twitter or email, and I find they often are, to help answer some questions. So beware, details are often missing. It's much better to have an existing code implementation to work against, or at least reference. So luckily we have 2 implementations. We have the original Google implementation in a library called Meliad. And this is kind of scattered, so it contains a few different papers, and the individual components are kind of scattered throughout the library. We also have this implementation from Lucid Rains, and this is a PyTorch implementation from Phil Wang, that's Lucid Rains' real name. He has implemented hundreds of papers. It's very clear, concise code. He's a great person to learn from. So I recommend you look through some of these implementations if you're curious to see what else is out there. So we're very lucky to be able to cross-reference and sometimes heavily borrow from his implementation. So check him out if you're interested in implementing papers and interested in best practices. Okay, step 1, complete. Step 2, identify paper idea, how they implement it, and how they will test it. So it's time to read the paper. If you're not super familiar with reading papers, I strongly suggest you don't go top to bottom, line by line. There's many more effective ways to read a long, often dense paper like this. And so what I find helpful is to read in passes. And this just means I'll do a first pass that is aimed at getting a very high level understanding, and with subsequent readings, I'll fill in more and more of the details as I go. So the first pass, as an example, I'll usually just read the abstract and take a look at the diagram, which usually details the architecture of the model, and then maybe some results. And with each subsequent reading, I'll fill in more and more of the details as I go. But this is a much more effective way than going top to bottom. So for our purposes, we're implementing this, so we need a lot of detail. So we'll do a few passes, and it'll take a while to read through the whole thing. Because we really need to understand this paper in great detail, I find it's helpful to come into the reading with some simple but important questions, and these should apply to almost any paper. So I definitely don't do this for every single paper I read because that would take forever, but if you can answer these questions, then you've got a really good understanding. These are also designed to help you think critically about the paper, and for me this helps a lot. So you might read a paper and even though you thought you understood it and everything seemed good, you might look back at the questions and begin to think critically. Actually, now that I reflect on this, I don't really think the problem as laid out by the authors is maybe that important. Or I don't think that what they actually do addresses the problem adequately. Or maybe the way they measure success doesn't really align with the stated problem. So there's all kinds of ways to lose track of the big picture, and these questions can just serve as a tool to help you think critically and stay on track with the big picture. And we'll actually see a couple examples for this paper of how these questions help us do just that, really interrogate what is going on. All right, so now it's time to read the paper. Surprise, I've read it before a few times, but it's likely that you haven't, so you should pause the video, read the paper, and if you like, try and answer these checklist questions, and then I'll go over my answer to these questions and discuss the paper. And after that, we can get started building. Okay, let's go over some of the questions that are used here to help us test our understanding of the paper. Okay, question 1. What's the idea in a sentence or two? I've got language models would benefit from a long-term memory mechanism. Approximate KNN lookup into non-differentiable memory of recent key-value pairs improves language modeling. So that's a very loaded couple of sentences. There's a lot to unpack, but to me that's a very concise formulation of what's going on in the paper. All right, what's the motivation as framed by the authors, and what's the problem they are solving? So attending to faraway tokens is important in many situations. However, transformer performance is limited by context window size. So to back up a little, think of ChatGPT. It has a limited context window. So a context window is how many tokens the model can attend to at once. At the time of watching this, I have no idea what the context window will be for you, but even now it's something like 64,000 or 32,000. State-of-the-art models have these very large context windows. But at one point, particularly when it just came out, you could only fit a few thousand tokens in, specifically 2048. So what does this mean? If you were reading a book and each chapter is 2048 tokens, you would read chapter 1, you would understand it, and then when it's time to read chapter 2, you basically have to throw out everything you know about chapter 1 just in order to make room for chapter 2, and so on for chapter 3 and 4. So obviously this isn't what we want. The obvious question you might have right now is, well, why don't we just increase the context window size? Why is this a limitation? And it's a great question. The reason why we don't just naively make the attention window bigger is because attention is a quadratic operation relative to the size of the input. So if we double the context window, we're actually quadrupling the compute requirements. And this doesn't just arbitrarily work. We would have to throw a lot of compute just to increase the context window to some arbitrary length. And there have been many, many attempts to fix this. At the time of this paper, even though now we have certain solutions to get around this, this was a real problem. And there were many attempts to solve it, and you can read about this, for example, in the related works section. There's a lot of sparse attention strategies, ways to modify attention, basically to get subquadratic complexity. And this is the motivation, as the authors propose, to increase what the model sees, and they're not going to use a sparse attention implementation. They're not going to just expand the context window. They're basically proposing we're going to add memory, and that's how we will address the context window problem. Question 3, how do they attempt to solve it? So I've got, they store key value pairs at one layer of the network. On future passes through the model, perform approximate KNN search into stored key values by using the current query projection, perform regular QKV attention at this layer, and also perform QKV attention a second time using the current queue and stored/retrieved key values. Then we combine these and pass them into the next layer as usual. So this is somewhat spelled out in the diagram here. So all of these layers are going to be regular. And then one of the layers, specifically the second to last layer, will do two things. It'll have two branches. One branch is going to perform self-attention as usual, and a second branch is going to do something a little different. The second branch basically takes the query projection, and it uses this to search previously stored key value pairs. So we do a KNN search with our query against the stored key value pairs, and we retrieve the most similar. The idea being that these are from some past segment of one long document. And so it'll be relevant if our query can actually attend to past segments of the document. So we pull those in and we perform self-attention, but with the retrieved key values. So we have these two branches of computation, two branches of attention, and then we combine these with a gating function, which is down here. But basically this gating function is, we'll look into more detail, it's as much as to say, you get to weigh these with a value between 0 and 1, and the opposite weight is 1 minus that value. So it can choose to attend half and half to the memorized attention and half to the regular attention, or it can basically split that weight, and it's a learnable parameter. So at one layer, we are incorporating some of attention based on past key value pairs. And of course, inside of here, at this layer, we'll take our current key values and we'll stick them into memory so that on future passes, we can pull those in at this layer. So that is kind of the core idea. Okay, what is the main contribution of the paper? I have the new approach as the main contribution. We retrieve the exact historical key value matrices rather than averaged or summarized versions of past content. And number two, gradients do not flow back into the KNN memory, making it fast and scalable. So this is spelled out here, and they even just say, this is what distinguishes our approach. So the first point I would say is maybe putting this paper in contrast to RAG or many RAG approaches. So RAG is retrieval augmented generation, and often the idea there is you do have an external memory, but it's not past key value pairs. It's something like an embedding vector of previous content. And then you use something in your network, something in your model, to run as a query against these past embeddings. So there's no averaged or summarized versions. We're directly pulling in and out the key value matrices. And the point two here is gradients do not flow back into KNN memory, making it fast and scalable. So you could back propagate into the memory, and this would essentially be like adding more parameters into your model. But if you have a very large memory, it's going to make it extremely slow and not scalable if you have to backprop into all of these potentially thousands, millions of vectors looking backwards. So they're non-differentiable. The improvement to language modeling and fine-tuning are probably the two other contributions here, where, let's pull up the paper. Basically, they note that on this specific data set, using perplexity as a measurement, a memorizing transformer with 1 billion parameters that has this extra memorizing component basically achieves the same perplexity as a regular transformer with 8 billion parameters. So a much smaller memorizing transformer does, on this specific benchmark, the same performance as a much larger transformer. So we can trade off scale for memory in this specific application. And the other kind of contribution here, I think, is fine-tuning, where you might think, okay, I have to train up a memorizing transformer from scratch. That could be very expensive. Actually, they find that if you take a regular transformer and you just fine-tune it with one of these memorizing layers, it pretty quickly will jump down to what you would have if you had begun a memorizing transformer from the very initialization. So basically, you can fine-tune the memorizing component without too much of a loss, and you don't have to expensively retrain an entire language model from scratch. Okay, the last two questions. How will they measure success, and were they successful? So, how will they measure success? We can look straight at the paper. And section 4 outlines the experiments that they'll use to evaluate whether or not this approach is successful. So, we evaluate the effect of adding external memory on 5 language modeling tasks, all of which involve long-form text. So, they're taking a few different data sets that contain very long articles, or they're just taking large text data sets and filtering out anything that's too small. The results show significant improvements in the perplexity of the model with the addition of external memory. And so, as we've seen before, were they successful? You can look at this and say, yes, in fact, you can get away with a much smaller model size with external memory and get per token perplexity equal to a larger model. So we've already looked at that. We've looked at the fine-tuning result. That's kind of a bonus. And we've seen some experiments that demonstrate what happens when you have different context sizes, different memory sizes, and the per token perplexity effect on all of these data sets. So it's demonstrating that yes, this in fact is a successful approach. Okay, here's a prime example of why having these checklist questions is actually a really good tool to help you think critically about the paper. So while I was going through these questions, the 2 success questions we just went over, I had a question of my own, which is, did this model outperform other models on long document data sets? So is this approach better on long document data sets? And you'll notice in the paper, there's no real comparison against other models. So we have these benchmark tasks, but the performance of other models isn't listed. So this is all variations of memorizing transformer with different context sizes, different memory sizes, the inclusion of an XL cache, which we'll talk about later. So aside from comparing to a vanilla attention model, we don't really know how this fares against other models that are designed to handle long context. The author addresses this in a video presentation, which I've included a link to. He just goes over the paper, the motivation, and there's some interesting discussion at the end with some of his colleagues. But what he says is as follows. This is not quite an appropriate thing to compare this work to a long-range, sparse attention method. So while both are an attempt to solve long-range context, sparse attention methods have a scaling issue. Say we want to expand our context to all of Wikipedia or all of the internet. You still have a scaling issue there because we don't want to have a context window that is millions of tokens long. Whereas memorizing transformers, in theory, is something that has a better chance of scaling in this sort of infinite direction. So it's not quite an apples to apples comparison because they have different goals. So I do buy this argument, but I'm curious anyways. So what we've done is picked out one of these data sets. Let me see if I can grab it here. So I've chosen PG19 and I looked at a few of these. And this is a large data set of English language books. And if you just type it into Google, you can find, for example, here's the original repo from DeepMind, and Hugging Face has a version of almost every data set. And inside of this, you can actually get a look at the data. So this is literally books, as you can see. Complete works of Shakespeare, The Warriors by Anna Robertson Brown Lindsay. And if you use this site, Papers to Code, it's not exhaustive, but you can find other models and other repos that use this data set. So I was able to actually find another paper. This is Long Range Language Modeling with Self-Retrieval from June 2023. And this does in fact benchmark on PG19. And they get ours 11.5, and they compare it to a few other models, and it's down to 10.5. And they even have gone to the trouble of including the memorizing transformers score here, which is 10.97, which is not what's in the memorizing transforming papers, so they must have implemented it and run it again and gotten a better score. Anyways, all of this to say, it doesn't look like the model is wildly better or worse than these other approaches designed to handle long-range context. So the range of perplexity is pretty small. Along the same line of thinking, I had a few more questions as I was reading about the success of the model and how we measure it. And so I've put these here, and maybe we'll investigate them once we've built the model and want to run some experiments. So all the reported metrics are perplexity, and this is a language modeling metric. But we might be interested in new capability that memory would unlock that doesn't exist without memory, or some kind of classification accuracy task, or really any kind of downstream applied performance that we could measure against a regular transformer or other models. And so I haven't looked too deeply into this, but I was able to find this pretty quickly. And it looks like question answering with long inputs, long document comprehension. So some kind of benchmark task like this could be really interesting to run. Other than that, how does external memory compare to expanding the context windows? So the author actually addresses this in the video, and it goes as follows. So he didn't include it in the paper, but a few kind of experiments on the side showed that, for example, if we have a 512 length context window and we have 1536 memory, we can compare this to just a 2048 size context window. And in terms of accuracy, these were about the same. And this is just from a couple sentences mentioned in the video. Obviously, for compute, I think it depends on the input sequence, but memorizing transformers and having a memory should be more efficient. And lastly, how does this compare to other models for regular length documents? Are there significant boosts in performance or language modeling or classification or anything downstream that result from having a memory? All right, it's time for step 3, identify components of the paper. So the components of the model that we'll be building, and we'll be spending the rest of the videos in this series building those out and eventually sticking them together. So I've got a section here, and I'll go through this a little fast, but we're going to read through the paper and pull out the things we need to build. And if you haven't read the paper, you should definitely do that and take your time in section 3, which is what we're going to look at. And this really spells out the details of the architecture. But for now, I'm going to go through and I'll pull out the main things that we need. And then in each of the subsequent videos, when it's time to build this component or that component, we'll spend a great deal of time actually looking into the details. So don't worry if we gloss through some of this. We'll get to the details eventually. Okay. The architecture of our transformer is shown in figure 2. The bulk of the model is a vanilla decoder-only transformer. So, vanilla decoder model. And you're out of luck if you don't know what that is. It's an example of where they don't tell you that much. It's assumed you know what that is. And we, of course, can look that up, and I'll show you what that is. Long documents are split into subsequences of 512 tokens, and each is used as input for one training step. In contrast to standard practice, we do not shuffle the subsequences. So we feed them in one by one next to each other. So usually when you're training, you want to shuffle them. But here, the whole point is that we'll be feeding in, say, some long document. We'll split it into segments, and we want to feed the segments in sequentially so that our KNN memory is holding on to previous sequences so we can test over a long document. Okay. We also use a transformer XL style cache, which holds the keys and values from the previous training step. When doing self-attention, the cached keys and values are prepended to the current keys and values, and we use a sliding window causal mask. Each token has a local context that includes the previous 512 tokens. So again, there's not a lot of detail here, and what we will do is go into the Transformer XL paper and see exactly what's going on. But the main idea is, in addition to the memory, we're also going to have XL style recurrence. So we'll feed in, say, segment 2. We're going to hold on to the key values of segment 1. And when we feed in segment 2, we're going to prepend those key values to the current key values in segment 2. So not a lot of detail here. We'll definitely get to it when we build that component. But that is going in our things to build list. XL attention layer. All right, and now we come to KNN, augmented attention layer, and this is kind of the main point of the paper. So one of the transformer layers near the top of the stack is a KNN augmented attention layer. It combines two forms of attention. One form is standard dense self-attention. It also does an approximate k-nearest neighbor search into the external memory. So, as I've explained before, there are two branches of computation. We have the regular dense self-attention. And then in the other branch, at this one layer, we take the query projections and we use them as our query against a database of key value vectors. And the most similar key value vectors, the most similar to the query projection, get pulled in, and we use those to perform attention. And this is at a per token basis. So it's done token by token. So the query projection has 512 tokens. We pull back 512 key value pairs, and we perform self-attention, and then we merge these two branches, and we merge it with a gate. And this is a per head bias gate, meaning that if we have 8 heads in our self-attention, each of these heads will be allowed to adjust how much it pays attention to the local attention, how much it pays attention, and how much weight it's giving to the memorized attention. So basically, these are learnable parameters, and our model will determine by itself through backpropagation how much it should be attending to the memorized form of attention versus the local current form. So that is something we'll need to build. We'll need to build both the KNN augmented layer, but we'll also need to build in the vector database. So we'll have to have KNN memory. And obviously, we'll have to add to this. So at each pass through this layer, we're going to add the key values into the memory. And of course, at some point, we're also going to have to remove them. Otherwise, this just gets larger and larger and larger, and we don't scale. So we'll have some kind of removal functionality that will be called, and it'll be up to us. They have a scheme in the paper, but we're going to go with something slightly different and slightly more conceptually straightforward. So add remove functionality here for the KNN memory. And they talk a little bit about batching. Figure 3 illustrates how multiple long documents of different lengths are packed into a batch and split into subsequences. So imagine we have a batch dimension size of 2, and we're feeding in these documents. These documents will be of variable length. The authors propose is that you have a separate memory for each batch dimension. And so each of these batch dimensions is functioning independently, and it only holds on to, say, all of the segments of document A. And when document A in batch dimension 1 is finished, it knows to clear and bring in document C. And the batch dimension 2 is also doing B and then D. So there are n memories for your n batch size. We'll go with something simpler. We'll just have one memory to start with because it's much easier to keep track of what's going on, and we can always add that complexity later. But that is their format, and that also obviously helps you scale because we'll be crushing everything into one memory, which should, in theory, work fine, except for scaling. It should work fine because if you are one segment of document A, say the 5th segment, you should really only be attending to previous segments of document A. Those should be relevant to you. So you shouldn't have to filter through the memory. But this is speculative. We'll build it out this way, and then we can make changes as we go. All right, I've digressed. KNN memory, add remove functionality, KNN augmented layer. And then we come here to position bias. So for dense attention within the local context, we use a T5 relative position bias. We don't use position bias for the retrieved memories. T5 bias puts all long-range tokens in the same bucket anyways. Once again, no explanation really of what this is. You have to go to the T5 paper and look at what their relative position scheme is. So we will do that, and we'll actually look a lot at relative position bias and position bias as a kind of sub-research field as a whole. So we'll get into a lot of detail about position encoding schemes. But that is something we will have to put in. T5 relative position embedding scheme. And let's see. Distributional shift. So this is a point that they make that as we're training the model, all of the weights are updating. So at the very first iteration, we will put some key values into memory. And those key values are a function of the model parameters, right? So we've projected, based on one input, the key value projections, we stick them into memory. As you train the model, these will update. So you could feed the same sequence through, say every 100 training steps. And the key value vectors put into memory would be different every single time because your model is updating. So the whole concept of similarity breaks down if you're using, at different time steps, a different model to embed these vectors. The distribution changes throughout time. So to address this, they normalize keys and queries. So the keys and queries will be normalized before they're put in at this layer. And this is just an attempt to mitigate the distributional shift. So we'll remember to put that in. That's more of a detail when it comes to the KNN layer. We are using approximate KNN, they're saying, and this gives us a recall of about 90%, so you don't need exact KNN. And they use face. We will also use face, and we'll look in much more detail at the choice of vector database, the choice of distance metric, and so there are actually a lot of things to configure and think about when we're building our vector database and how we want to search through it. And that should be about it. In the experimental method section, they actually have a lot of detail about the size of the model. Okay, we're using k equals 32 for our top k retrieval in the KNN memory layer. And we have a 12-layer decoder only transformer, the number of attention heads, embedding size, which optimizer. So they've actually included a lot of details of the kind of hyperparameters and the parameters of the model itself. So that's a good rundown of the high-level components that we need to build when we're putting this model together. All right, so what have we got? Let's go back to our checklist, our plan, and we are on step 4. So we've identified the components and now have a rough pseudocode understanding of how things work and fit together. So what do we have here? It's a vanilla decoder model. And what that means, it's basically a GPT-like model. At each layer, there's XL attention, so there's recurrence at each layer. So we'll have to hold on to previous key value pairs for each segment and prepend them. In addition, one of the layers will have KNN capability, and so it will talk to a KNN memory that we need to build. And lastly, we'll have a different kind of relative position embedding scheme, and that will work at every single layer. So we have a rough kind of idea of how these things fit together, and that's going to guide us. And as we build each component, we're going to think more about how these things fit together. But for now, we're ready to start building. And I have a few tips for building effectively that probably apply to most of software, but they're good to keep in mind here. So try to build the simplest thing possible and then add in complexity. So we're even doing that here as we will build a vanilla transformer layer, which is just a standard dense self-attention decoder layer. And then we'll add in the complexity. So then we'll add in XL recurrence, and then we'll add in a KNN component. Make things work first and focus on performance last. So we're not going to focus on, for example, optimizing the KNN memory, even though we know it's probably going to be slow with our first pass. We're going to make everything work, and then we can come back and think about performance later. So we don't want to optimize early. We also want to think about how we test it. So we want to work out a metric and a goal before we start. And we want to make testing this model or testing each component really simple, repeatable, fast, so we can iterate quickly and measure progress. So those are just a few tips for building effectively. Well done. The preliminaries are out of the way. So we've gone through what is essentially a lecture on how to implement a paper. We've looked at a paper. And now in the next video, it's time to finally start building.